Hey guys, tonight we're diving into a cosmic question that probably keeps very few of you up at night, but maybe, just maybe, it should. Will our sun, that big fiery ball of comfort and vitamin D, ever morph into a black hole? You're probably picturing it now, that warm, reassuring glow suddenly collapsing inward, sucking up everything in its path, including, well, you. Good news, you probably won't survive to see it, so there's that. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Now, dim the lights and let's ease into tonight's journey together. You're lying there, feeling the quiet hum of your room, perhaps the distant murmur of city life, or maybe just the gentle rustle of leaves outside your window. It's dark, or at least it's supposed to be. But if you were somehow capable of seeing through the solid rock beneath you, through the molten core of our planet, and out into the vast emptiness, you'd find it there, the sun. Right now, in this very instant, it's a brilliant, stable star, a main sequence star, as astronomers like to call it. It's been doing its thing for about 4.6 billion years, tirelessly fusing hydrogen into helium in its core, converting mass into energy with an efficiency that would make any power plant operator weep with joy. This process, nuclear fusion, is what powers literally everything on Earth, from the photosynthesis in a tiny blade of grass to the warmth on your skin when you step outside on a sunny day. Imagine for a moment that you are tiny, even tinier than an atom, and you're floating somewhere deep within the sun's core. The pressure is unimaginable, so intense that it would squash you flatter than a cartoon pancake. The temperature? We're talking millions of degrees Celsius, hot enough to strip electrons from atoms, creating a superheated plasma. It's a ballet of protons colliding, eventually forming helium nuclei, and in the process releasing a tiny bit of energy. Multiply that tiny bit by zillions of zillions, and you get the incredible luminosity of our star. This golden orb, our star, is essentially a giant, self-sustaining nuclear reactor, but a remarkably well-behaved one. It's in a delicate balance, a cosmic tug-of-war. The immense gravitational pull, constantly trying to collapse the sun inward, is perfectly counteracted by the outward pressure generated by all that nuclear fusion in its core. It's like trying to squeeze a water balloon with one hand while simultaneously inflating it with the other. A very, very big water balloon. This equilibrium is what gives the sun its longevity and its steady glow. If fusion were to slow down, gravity would win, and the sun would begin to shrink. If fusion sped up, the sun would expand. But for billions of years, it's held this perfect pose, allowing life to flourish on our little blue marble. You know, it's a funny thing to consider how utterly dependent we are on this celestial furnace. Every breath you take, every bite of food you eat, every drop of water you drink, it all in some way traces back to the sun's energy. It's the ultimate energy source, far beyond any coal-fired plant or wind turbine. And yet, we rarely give it a second thought, do we? It just is. It rises, it sets, and we go about our lives, blissfully unaware of the incredible physics happening 93 million miles away. This incredible stability is why we're even here, why evolution could take its sweet time, developing everything from single-celled organisms to complex beings like you, currently listening to this. It's a mainstream historical fact, though perhaps more accurately a scientific fact, that without the sun's consistent energy output, Earth would be a frozen, lifeless rock hurtling through the dark. Think of the bizarre, quirky tidbit that early civilizations, like the Egyptians, literally worshipped the sun as a deity, Ra, the creator god. They intuitively understood its life-giving power, even if they didn't quite grasp the nuclear fusion part. You almost have to admire their directness, don't you? Sun gives life, therefore sun is God. Makes more sense than some modern beliefs, if you ask me. And speaking of beliefs, historians still argue whether the precise alignment of ancient structures, like Stonehenge, truly served as sophisticated solar calendars, or if some of it was simply coincidental. Regardless, the sun has always captivated humanity, inspiring awe, fear, and wonder. From ancient sundials to modern solar panels, our relationship with this star has shaped our societies and our understanding of the universe. It's a constant, reassuring presence, a cosmic anchor in a vast, ever-changing cosmos. But like all things, even anchors can shift. Our comfortable sun, as stable as it is, isn't immortal. It's merely in a particularly long-lasting phase of its life. Like any living thing, even stars have a birth, a life, and eventually a death. And it's that eventual demise that we'll be peeking into next, easing our way into the truly mind-bending possibilities of stellar evolution.
So, you're nestled in your blankets, perhaps still pondering that giant hydrogen balloon we call the sun. We just talked about its current serene existence, a perfect balance of gravity and fusion. But here's the cosmic spoiler. Nothing lasts forever, not even stars. And our sun, bless its bright heart, is no exception. To truly understand if it can ever become a black hole, we first need to zoom out. We need to grasp the universal life cycle of all stars, because every star follows a cosmic blueprint that dictates its ultimate fate. Think of it like a grand celestial play, with different stars taking on different roles, some short-lived and explosive, others long and slow. Every star, from the smallest red dwarf to the most colossal hypergiant, begins its journey in essentially the same way, as a vast cloud of gas and dust. We're talking about nebulae here, those breathtaking cosmic nurseries you see in all the fancy space pictures, often glowing with vibrant colors like the Orion Nebula. Imagine yourself as a tiny speck of cosmic dust chilling out in this enormous, frigid cloud. Due to slight variations in density, or perhaps a cosmic nudge from a passing supernova shockwave, it's a rough neighborhood out there. Gravity starts to assert its dominance. Little by little, gas and dust particles begin to clump together. It's a slow, inexorable process, like a cosmic snowball rolling downhill, picking up more and more material. As more mass accumulates, the gravitational pull strengthens, drawing in even more matter. This growing lump of matter starts to contract and spin, forming a denser and denser core. This is what we call a protostar, essentially a baby star that hasn't quite ignited its fusion engine yet. Now, as this protostar contracts, the pressure and temperature in its core dramatically increase. This isn't just a gentle warming, it's getting seriously hot and incredibly dense. Think of a bicycle pump. When you push the handle down, the air inside gets compressed and heats up. Now scale that up by, a few zillion times, and you've got a protostar. This heating continues until the core reaches an absolutely critical temperature and pressure, about 15 million degrees Celsius. At this point, something magical and profoundly energetic happens. The hydrogen atoms in the core start to fuse into helium. This is the moment a star is truly born, igniting its nuclear furnace and settling on to what astronomers call the main sequence. Our sun has been on this main sequence for billions of years, living its best stable life. It's the longest phase of a star's existence, where it achieves that perfect balance we discussed earlier, burning hydrogen steadily. The duration a star spends on the main sequence depends entirely on its mass. This is a crucial point, so lean in. Smaller stars, like the tiny red dwarfs, are incredibly frugal with their fuel. They sip at their hydrogen like a really slow drinker at a party and can last for trillions of years. Yes, trillions, far longer than the current age of the universe. They are the marathon runners of the cosmos. Our Sun, being an average-sized star, is more like a brisk jogger. It has a main sequence lifespan of roughly 10 billion years. Since it's already 4.6 billion years old, it's about halfway through its comfortable middle age. Larger stars, however, are like cosmic teenagers with too much pocket money. They are extravagant, burning through their hydrogen fuel at an astonishing rate due to their immense gravity and higher core temperatures. They are the sprinters, burning incredibly bright and hot, but their lives are fleeting, lasting only a few million years before they exhaust their fuel. It's a mainstream historical fact that stellar luminosity is directly related to mass, meaning more massive stars are exponentially brighter. Once a star exhausts the hydrogen fuel in its core, the delicate balance is broken. Without the outward pressure from fusion, gravity starts to win, and the core begins to contract again. This contraction heats up the layers surrounding the core, igniting a shell of hydrogen fusion around the now inert helium core. This new burst of energy causes the outer layers of the star to expand dramatically and turn it redder. At this point, the star enters its red giant phase. This is the grim future awaiting our Sun, but we'll get to that fiery inferno in the next section. Now, here's a quirky little tidbit. Did you know that some protostars never actually become full-fledged stars? If a collapsing cloud of gas and dust doesn't gather enough mass to ignite nuclear fusion in its core, it needs about 8% of the Sun's mass to pull off this trick. It becomes a brown dwarf. These are often called failed stars or substellar objects. They're too big to planets but too small to stars, and they just sort of fizzle out, glowing dimly from residual heat like a dying ember. Imagine a celebrity who gets all the pre-fame hype but never quite make it big. That's a brown dwarf for you. They're fascinating because historians still argue whether brown dwarfs should be classified alongside planets or stars given their unique characteristics and the blurry line between them. It's a debate that highlights how complex cosmic classification can be, far beyond our simple star, planet, moon categories. So, every star's life is a story written in mass. That initial mass dictates its entire destiny, from its brightness and lifespan to its dramatic final act. And it's that final act, particularly for stars much, much more massive than our Sun, that leads to the truly exotic phenomena, like black holes. But before we get there, we need to witness our Sun's own transformation, a transformation that will radically alter our solar system, perhaps even more profoundly than you might imagine.
All right, you're still there, right? Drifting through the cosmic possibilities, thinking about how stars, even our own Sun, aren't the eternal beacons we sometimes imagine. We've traced their birth and their stable main sequence lives. Now let's talk about the big change coming for our comfortable Sun, a transformation that will irrevocably alter our inner solar system. We're about to witness its inevitable transition into a red giant. This isn't just a slight adjustment, it's a dramatic, planet-swallowing expansion. Picture this. Billions of years from now, our Sun has used up almost all the hydrogen fuel in its core. That magnificent nuclear furnace we talked about, the one tirelessly fusing hydrogen into helium, starts to sputter. It's like your car running out of gas.
The engine doesn't just stop immediately. It might cough and splutter a bit before grinding to a halt. In the Sun's core, with hydrogen depleted, nuclear fusion ceases, and gravity, that relentless force, begins to win the tug-of-war. The helium core starts to contract under its own immense weight. As this core shrinks, it heats up intensely. This isn't fusion heating, it's purely gravitational compression. This superheated, contracting core then starts to cook the layer of hydrogen surrounding it, which until now has been relatively untouched. This is called shell hydrogen fusion. This shell fusion is much more energetic than the core fusion that sustained the Sun for billions of years. Imagine putting a new, more powerful engine in your car. This burst of energy generates an enormous outward pressure, pushing the Sun's outer layers far, far beyond their current boundaries. The Sun begins to inflate like a massive cosmic balloon being overinflated. As these outer layers expand, they cool down, which is why the Sun will take on a reddish hue, hence red giant. It's a bit counterintuitive, isn't it? Getting bigger makes it cooler on the outside, a bit like stretching a hot piece of taffy until it thins out and cools. This expansion will be truly monumental. The Sun, currently about 1.4 million kilometers in diameter, will swell to encompass Mercury, then Venus, and quite possibly Earth itself. Think about that for a moment. The very ground you're lying on, the air you're breathing, the planet that cradles all known life, could be engulfed by the expanding inferno of our own star. It's a mainstream historical fact that studies of stellar evolution predict this fate for Sun-like stars. We're not just guessing here. Astronomers observe this happening to other stars throughout the galaxy, stars that are further along in their life cycles. So, what does this look like from, say, Mars, if it still exists and is not also a cindered husk? The Sun would no longer be a distant, brilliant disk. It would fill a significant portion of the Martian sky, a gargantuan, fiery red orb casting an ominous glow. The surface of whatever remains of Earth would be baked beyond recognition, its oceans long boiled away, its atmosphere stripped bare. Any intrepid space explorers a few billion years from now would find a very different, very hostile inner solar system. There's a quirky tidbit about this process. As the Sun expands, it actually loses mass. How does that happen, you ask? As the outer layers puff out, they become less gravitationally bound to the core. The Sun's solar wind, a constant stream of particles flowing out from its surface, will become much more intense, effectively blowing off vast amounts of its outer atmosphere into space. It's like a giant cosmic shedding, leaving behind a significantly less massive core. This mass loss has implications for the orbits of the remaining planets, pushing them slightly outward as the Sun's gravitational grip weakens. So, while Earth might be swallowed, if it just barely avoids being engulfed, its orbit would certainly expand. Historians still argue whether the precise timing of this red giant phase could be slightly influenced by extremely subtle factors, like the Sun's rotation rate, but the general timeline and outcome are well established. Imagine the sheer scale of this transformation. From a comfortable yellow dwarf, our Sun will become a bloated, menacing behemoth. The light it emits will be different, skewed towards the red end of the spectrum, giving our future sky a perpetual twilight glow, if there's anything left to see it. It's a chilling thought, isn't it? The source of all life becoming its ultimate undoing, at least for our planet.
This red giant phase won't last forever, thankfully for any theoretical survivors on, say, Jupiter's moons. It's a relatively brief, albeit dramatic period in a star's life, lasting only a few 100 million years, a blink of an eye compared to the billions it spent on the main sequence. It's the stellar equivalent of a final big sigh before settling into its long, quiet retirement. And what comes after this explosive expansion? That's where our story takes another fascinating turn, leading us closer to understanding what our sun's ultimate fate will really be. But first, let's consider the truly dire consequences for our home planet and its neighbors during this fiery expansion.
All right, you're still with me, perhaps with a slightly unsettling image of our sun as a monstrous planet-gobbling giant. We've set the stage for its red giant transformation. Now, let's really lean into the unsettling part. What actually happens to Earth, Mars, and the rest of the inner solar system when our sun goes full Godzilla? The planetary fates of our neighboring worlds are about to be definitively decided. As the sun swells, its outer layers will push outwards relentlessly. Mercury, being the closest planet, is absolutely toast. It will be the first to be completely engulfed and vaporized. Imagine standing on Mercury right now, if you could, which you can't because it's already scorching hot. Billions of years from now, that little rock will simply cease to exist, absorbed into the sun's expanding atmosphere, its atoms mingling with the very star that once illuminated it. It's a pretty definitive end, wouldn't you say? Venus is next in line. Currently shrouded in a thick, toxic atmosphere, it's already Earth's hotter, nastier sibling. When the sun expands, Venus will share Mercury's fate, though perhaps with a little more dramatic flair, as its dense atmosphere boils away before its rocky core succumbs. It's like throwing a snowball into a bonfire. It won't last long. And then there's our beloved Earth. This is where it gets particularly grim. The generally accepted scientific consensus, a mainstream historical fact, is that the sun will expand beyond Earth's current orbit. Our blue marble, the cradle of life, will be engulfed. Before that happens, though, the heat will become unbearable. Long before the sun's edge reaches us, Earth will experience runaway greenhouse conditions, far worse than anything climate scientists currently warn about. The oceans will boil away, first slowly, then with incredible ferocity, turning into superheated steam that escapes into space. The atmosphere will be stripped away, the surface will become molten rock, and any life, from the tiniest microbe to the most complex ecosystem, will be utterly extinguished. The pale blue dot will become a glowing red cinder, then a vaporized ghost within the sun's expanding envelope. It's a truly final farewell. However, here's where a tiny, almost academic debate exists, a quirky tidbit for you. Some models suggest that as the sun loses mass during its red giant phase, remember that cosmic shedding we talked about, its gravitational pull on Earth might weaken just enough to push our planet's orbit slightly outward. If Earth moves far enough, fast enough, there's a slim chance it might escape direct engulfment. But even in this highly optimistic scenario, the Earth would still be utterly uninhabitable. It would be a barren, roasted husk orbiting a vastly expanded, albeit less massive, red giant. The surface would be a sea of molten rock, perhaps with exotic minerals forming under extreme temperatures and pressures. So, while it might not be literally inside the sun, it would be no picnic, more like a cosmic hot plate.
Historians still argue whether the subtle interplay of mass loss and orbital expansion could truly save Earth from direct engulfment. But practically speaking, the outcome for life remains the same. Game over, man. What about Mars? Currently, it's a cold, dusty desert. Its fate is less certain. It sits further out, so it has a better chance of avoiding direct engulfment. However, it will still experience extreme heating. Any residual ice or water on Mars would vaporize, and its already thin atmosphere would be severely impacted. It might escape becoming part of the Sun, but it would transform into a superheated, barren rock, perpetually bathed in the dim, reddish glow of the bloated Sun. It won't be the picturesque red planet we know, but a much more intense version. Beyond Mars, the asteroid belt and the gas giants, Jupiter, Saturn, Uranus, Neptune, would likely survive the red giant phase relatively intact, though their environments would change drastically. Jupiter's moons, particularly Europa and Ganymede, which currently harbor vast subsurface oceans, might actually warm up considerably. This could potentially make them more hospitable for a time, melting their icy crusts and creating transient liquid water environments on their surfaces. Imagine, if you will, the last vestiges of the solar system's habitability shifting to the moons of the outer planets, perhaps even briefly allowing for some exotic, extremophile forms of life to emerge or adapt, before the Sun finally shrinks into its next phase. It's a strange thought, isn't it? Our solar system's habitable zone migrating outward. The sheer scale of this planetary destruction is difficult to truly grasp. The very essence of what makes Earth home, its temperate climate, its liquid water, its protective atmosphere, all vanish. It's a stark reminder of the immense power of stars and the cyclical nature of the cosmos. Our Sun, the bringer of life, will eventually become the bringer of ultimate destruction for its interplanetary family. But this destructive phase, thankfully, is just a transition. The Sun won't just stay a red giant forever, cooking planets. It has one more significant act to play before settling into its long, quiet retirement. And that retirement, as we'll explore next, will look very, very different from its current glory.
Okay, deep breaths. The thought of Earth being roasted and vaporized by our own Sun is a bit much before bedtime, I know. But thankfully, that red giant phase, while dramatic for our inner solar system, is temporary. The Sun, after its bloated, fiery period, will undergo one more significant transformation, shedding its outer layers to reveal a tiny, incredibly dense, and ultimately fading ember. This is where our Sun becomes a white dwarf. So imagine our red giant Sun having expanded and shed a significant portion of its mass through that enhanced solar wind we talked about. Eventually, it runs out of fuel for even that shell fusion. The last vestiges of its energy production cease. Without any outward pressure from fusion, gravity takes over completely in the core. But here's the crucial difference. The Sun, being a relatively low-mass star, isn't massive enough to create the conditions for further nuclear reactions beyond helium fusion, which it briefly does, converting helium to carbon and oxygen before running out of that fuel too. It simply doesn't have the gravitational punch to squeeze its core tightly enough to ignite heavier elements. Instead, the core contracts, becoming incredibly dense. It shrinks down to roughly the size of Earth, maybe even a bit smaller, while still containing about half of the Sun's original mass. Think about that for a second. A mass equivalent to hundreds of thousands of Earths squashed into a sphere no bigger than our planet. This density is almost unimaginable. A teaspoon of white dwarf material would weigh several tons here on Earth. It's so dense that the electrons in its atoms are squished together so tightly that they generate an outward pressure, a quantum mechanical phenomenon called electron degeneracy pressure. This pressure is what finally halts the gravitational collapse. It's a bit like trying to pack a stadium full of people, but they all suddenly gain personal force fields that repel anyone getting too close. This force field, on an atomic level, is what holds the white dwarf up against the relentless pull of gravity. This incredibly dense, superheated core is the white dwarf. When it first forms, it's still searingly hot, glowing intensely white due to its residual thermal energy. It's not producing new energy through fusion, it's simply radiating away the immense heat trapped within its compacted core. Over unimaginably long timescales, this white dwarf will slowly, majestically cool down. It's like a cosmic ember, gradually fading from a brilliant white to a dull red, and eventually, over trillions of years, becoming a cold, dark black dwarf. This theoretical black dwarf phase is largely conceptual because the universe simply isn't old enough for any white dwarfs to have cooled down completely yet. It's a mainstream historical fact that the existence of black dwarfs remains a theoretical prediction, as the universe's current age, around 13.8 billion years, is far too short for even the oldest white dwarfs to have cooled to that state. So, the Sun's ultimate fate, the end of its stellar journey, is to become a white dwarf. It's a gentle, quiet fading compared to the explosive deaths of much larger stars. It won't go out with a bang, but with a prolonged, almost imperceptible whimper, becoming a tiny, super-dense relic of its former glory. Here's a quirky tidbit for you. White dwarfs are often found surrounded by what's left of their planetary nebulae, the beautiful ethereal shells of gas and dust that the red giant shed during its expansion. These nebulae are some of the most stunning objects in the night sky, glowing in vibrant colors as the intense ultraviolet radiation from the hot white dwarf ionizes the gas. It's like a star's last spectacular hurrah, leaving behind a colorful cosmic monument before settling into its long, slow decline. This expelled gas is what allowed elements created within the star, like carbon and oxygen, which form in the brief helium fusion phase, to be scattered into space, enriching the interstellar medium for future generations of stars and planets. Historians still argue whether the precise chemical composition of these planetary nebulae can tell us even more about the internal processes of the dying stars. The process of a star like our Sun becoming a white dwarf is the most common stellar end state in the universe. Most stars are not massive enough to do anything more dramatic. It's a predictable, well-understood path for stars in our Sun's mass range. This gentle, drawn-out cooling is in stark contrast to the truly cataclysmic events reserved for the biggest stars in the cosmos, stars that have a very different, much more violent way of saying goodbye. And it's those spectacular, destructive farewells that can sometimes lead to the formation of the universe's most enigmatic objects, black holes. But before we leap into those gravitational behemoths, let's take a moment to understand the sheer scale of the explosions that precede them.
All right, we've tucked our Sun into its eventual white dwarf bed, a dense, slowly cooling ember, light years away from ever becoming anything so dramatic as a black hole. But this journey into cosmic finales would be incomplete without discussing the true fireworks of the universe, supernova. These are the stellar equivalent of dropping a mic, blowing up the stage, and then dissolving into a cloud of highly energetic particles. They are, quite literally, the biggest explosions in the cosmos, capable of outshining entire galaxies for a brief period. Unlike our Sun, which will gently shed its outer layers, a supernova happens to stars that are significantly more massive. We're talking about stars at least 8 to 10 times the mass of our Sun, often much, much larger. These colossal stars live fast and die young. Remember how we said bigger stars burn through their fuel much quicker?
Well, when these giants run out of hydrogen in their core, and then helium, and then carbon, and so on, they start fusing heavier and heavier elements. They become like cosmic onion layers, with progressively heavier elements fusing in shells closer to the core. Hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon. Each stage generates less energy and happens faster than the last. This furious race continues until the star tries to fuse iron in its core. And here's the crucial universe-altering catch. Fusing iron doesn't release energy, it consumes it. Iron is the ultimate dead end in stellar fusion. It's like trying to get your car to run on pure negative energy. Once the core becomes predominantly iron, there's no longer any outward pressure from fusion to support the immense weight of the star's outer layers. Gravity, having been held at bay for millions of years, suddenly and catastrophically wins. The core collapses in on itself with unbelievable speed in mere milliseconds. This sudden implosive collapse is the trigger for the supernova. As the core shrinks to an incredibly dense state, far beyond even a white dwarf, it rebounds violently. Imagine compressing a giant spring and then suddenly releasing it. This rebound, combined with a flood of tiny ghost-like particles called neutrinos that are suddenly released from the super-dense core, creates an outward-moving shockwave. This shockwave rips through the star's outer layers at incredible speeds, blowing them apart in a spectacular explosion. This explosion is what we see as a supernova. It's a mainstream historical fact that supernovae are crucial for life. Almost all the elements heavier than iron, including the oxygen you breathe, the carbon that forms your body, the calcium in your bones, and even the gold in your jewelry, were forged in the fiery heart of a massive star and then scattered across the cosmos by a supernova explosion. Without these cosmic element factories and their dramatic demise, the universe would consist mostly of hydrogen and helium, a rather boring and lifeless place. So, in a very real sense, you are made of stardust, specifically supernova dust. Kinda puts your morning coffee into perspective, doesn't it? Now for a quirky tidbit. There are different types of supernova. The one I just described from the collapse of a massive star is called a Type 2 supernova. But there's another fascinating kind, a Type 1a supernova. This one involves a white dwarf in a binary system, meaning it has a companion star. If the white dwarf siphons off enough material from its companion, it can eventually exceed a critical mass limit known as the Chandrasekhar limit, about 1.4 times the mass of our Sun. When it crosses this threshold, it reignites runaway nuclear fusion in its core, leading to a thermonuclear explosion that obliterates the white dwarf entirely. These Type 1a supernova are incredibly important because they all explode with almost the same intrinsic brightness, making them standard candles that astronomers use to measure vast cosmic distances and even discover the accelerating expansion of the universe. Historians still argue whether Type 1a supernova are truly uniform in brightness or if subtle variations exist that could impact our cosmological measurements. It's a fascinating ongoing debate at the cutting edge of astrophysics. The energy released in a supernova explosion is mind-boggling. It can be more energy than our Sun will produce in its entire 10 billion-year lifetime, all released in a matter of weeks or months. For a brief period, a single supernova can be as bright as an entire galaxy containing hundreds of billions of stars. If a supernova were to occur too close to Earth, say within 50 light-years, it would be devastating, potentially stripping away our ozone layer and exposing life to harmful radiation. Thankfully, there are no stars close enough to pose such an immediate threat to us right now. What's left behind after a supernova depends on the initial mass of the star. For stars that were, say, 8 to 25 times the mass of the Sun, the core doesn't just disappear. It collapses further, forming something even more exotic and dense than a white dwarf, a neutron star. We'll delve into those incredible cosmic relics next. But the key takeaway from supernova is this: they are the universe's ultimate fireworks, responsible for scattering the building blocks of life across the cosmos. Without them, we wouldn't be here, pondering our cosmic origins.
All right, we've witnessed the spectacular, galaxy-eclipsing glory of a supernova. It's the universe's most explosive way of saying goodbye. But what about the cosmic leftovers? When those massive stars, the ones roughly 8 to 25 times the mass of our Sun, detonate, their cores don't just vanish into thin air. They undergo an even more extreme collapse, leading to the formation of incredibly dense, bizarre objects known as neutron stars. These are truly cosmic relics, remnants of immense power. Imagine that core, having just gone through the iron crisis, collapsing under its own immense gravity. It's crushing down beyond the white dwarf stage, where electron degeneracy pressure halts collapse. Here, the gravity is so overwhelming that it forces electrons and protons to literally merge, squeezing them together to form neutrons. This is where the name comes from. It's a star made almost entirely of neutrons, packed together with no empty space. Think about that for a second. The very building blocks of matter forced into a new fundamental state. It's a bit like taking all the air out of a sponge until it's just a solid, squashed block. The density of a neutron star is almost beyond comprehension. We're talking about a mass greater than our entire Sun, compressed into a sphere only about 20 kilometers, 12 miles in diameter, roughly the size of a medium-sized city, like Toronto, where I am right now. If you could take a single teaspoon of neutron star material, it would weigh billions of tons. Imagine holding something heavier than Mount Everest in the palm of your hand. That's a neutron star. If you dropped a marshmallow onto a neutron star, it would hit with the force of 1,000 hydrogen bombs, vaporizing instantly due to the star's incredible gravity. It's truly mind-bending. This extreme density gives them an incredibly powerful gravitational field, second only to that of a black hole. Now, because the core retains its angular momentum as it collapses, neutron stars spin incredibly rapidly. Just like an ice skater pulling in their arms to spin faster, a star that once rotated leisurely over weeks or months can, upon collapsing into a neutron star, spin hundreds or even 1,000 times per second. This rapid rotation, combined with their incredibly strong magnetic fields, trillions of times stronger than Earth's, makes them behave like cosmic lighthouses. As they spin, they emit powerful beams of radiation from their magnetic poles. If one of these beams sweeps across Earth, we detect it as a regular pulse of radio waves, hence their common name, pulsars.
It's a mainstream historical fact that the discovery of pulsars in 1967 by Jocelyn Bell Burnell and Anthony Hewish was one of the most exciting astronomical breakthroughs of the 20th century. Initially, the incredibly precise repeating signals were so regular that they were jokingly nicknamed LGM-1 for Little Green Men 1, leading some to speculate about alien intelligence. Of course, they turned out to be natural phenomena, but what a quirky tidbit of history, right? The universe always finds a way to be stranger than fiction. The surface of a neutron star is also incredibly exotic. It's thought to be a super-dense solid crust of iron, beneath which lies a superfluid sea of neutrons, with perhaps some protons and electrons still floating around. Deep within the core, the conditions are so extreme that physicists aren't entirely sure what happens. It might be an even more exotic state of matter, perhaps quark matter or other theoretical particles. Historians still argue about the precise internal structure of neutron stars and what happens at their very cores, as direct observation is impossible and simulations are incredibly complex. It's one of the great mysteries of astrophysics. So, neutron stars are astonishing remnants of massive stars, born from the fiery crucible of a supernova. They are the densest objects in the universe that we can directly observe. But what if the star that collapses is even more massive? What if the gravitational pull is so utterly overwhelming that even electron degeneracy pressure, or neutron degeneracy pressure, the force preventing neutron stars from collapsing further, isn't enough? That, my friends, is when we cross the threshold into the realm of the truly mysterious and terrifying, the black hole, the universe's ultimate gravitational traps, where the very fabric of space-time is warped beyond recognition. And that, naturally, is our next destination.
All right, we've navigated the stunning destruction of supernovae and marveled at the impossible density of neutron stars. Now prepare yourself for the main event, the cosmic heavyweight champion of gravitational pull, the universe's ultimate trap, black holes. These aren't just dense. They are regions of space-time where gravity is so incredibly intense that nothing, not even light, can escape once it crosses a certain boundary. It's like the universe's most extreme one-way door. So, what exactly is a black hole? It's not really a hole in the traditional sense or an empty void. Instead, it's an incredibly concentrated amount of mass in an unbelievably tiny volume, creating an extreme curvature in the fabric of space-time itself. Imagine placing a bowling ball on a stretched rubber sheet. It creates a dip. Now imagine placing a supermassive cannonball on that same sheet. The dip becomes a deep, steep well. A black hole is like an infinitely deep, infinitely steep well in space-time. The surface of a black hole, the point of no return, is called the event horizon. Once something crosses this boundary, it's gone forever, pulled inexorably towards the center. No signal, no light, no information can ever escape from within the event horizon, which is why they are black. You can't see them directly. You can only detect their presence by their gravitational influence on surrounding matter, or by the fiery dance of gas being pulled into their maw. The concept of an object so massive that light couldn't escape actually dates back to the late 18th century, a quirky tidbit of scientific history. John Michel, an English geologist and astronomer, and Pierre-Simon Laplace, a French mathematician, independently speculated about such dark stars using Newtonian gravity, long before Einstein's theories of relativity came along. They were remarkably prescient, considering they didn't have the full picture of how gravity truly works. This demonstrates a mainstream historical fact. Sometimes revolutionary ideas are conceived long before the theoretical framework fully supports them.
The modern understanding of black holes, however, comes directly from Albert Einstein's general theory of relativity, which describes gravity not as a force, but as a curvature of space-time caused by mass and energy. When an object is dense enough, this curvature becomes so extreme that it effectively creates a well from which nothing can climb out. The region within the event horizon is disconnected from the rest of the universe, at least in terms of outgoing signals. There are different types of black holes, categorized by their mass. We're primarily focusing on stellar mass black holes tonight, which are formed from the collapse of massive stars. Then there are supermassive black holes, which reside at the centers of most galaxies, including our own Milky Way, and can have masses millions or even billions of times that of our Sun. Finally, there are theoretical primordial black holes, which might have formed in the very early universe, though their existence is still being debated. Historians still argue whether primordial black holes played a significant role in the very early universe's evolution. So, for a star to become a stellar mass black hole, it needs to be truly gargantuan. We're talking about stars that were originally at least 25 to 30 times the mass of our Sun, often even more. When these super heavyweights run out of nuclear fuel and their iron cores collapse, even the neutron degeneracy pressure that supports a neutron star isn't strong enough to withstand the relentless inward pull of gravity. The collapse continues past the neutron star stage, squeezing all the matter into an infinitely small point called a singularity. This singularity is where all the mass of the original star is concentrated. It's a point of infinite density where the laws of physics as we currently understand them break down. Imagine the chaos, the sheer violence of that final collapse. It's not just an explosion outwards, it's an implosion inwards, so powerful that it overwhelms everything, even the fundamental forces that hold matter together. The creation of a black hole isn't pretty, but it is undeniably fascinating. And it's a direct consequence of a star's starting mass. Which brings us back to our Sun. You can probably already guess where this is going, can't you? Our Sun is just too much of a lightweight for this kind of dramatic universe-bending exit. But we'll formalize that understanding next, truly cementing why our comfy star will never join the ranks of these cosmic giants.
All right. We've peered into the terrifying abyss of black holes, understanding their immense gravitational power and the concept of that point of no return, the event horizon. Now, let's connect the dots and explore precisely how these gravitational monsters are born, the formation of stellar black holes. It's a tale of colossal stars, ultimate collapse, and the universe's most dramatic transformations. This is where the universe truly pushes the limits of density and gravity. So, a stellar black hole doesn't just pop into existence out of nowhere. It's the spectacular yet inevitable end state for the most massive stars in the cosmos. We're talking about stars that were born with an initial mass of at least 25 to 30 times that of our Sun, though some models push that number even higher, towards 40 or even 50 solar masses to guarantee a black hole remnant. These are the titans of the stellar nursery, burning incredibly bright and fast, living lives measured in mere millions of years rather than billions. Recall our discussion of stellar life cycles. These supermassive stars, much like our Sun, spend most of their lives fusing hydrogen into helium in their cores. But their immense mass means their cores are under far greater pressure and heat. This allows them to continue fusion through progressively heavier elements once the hydrogen runs out. They burn through helium, then carbon, then neon, oxygen, and finally silicon.
Each of these fusion stages produces energy, creating the outward pressure that counters the inward pull of gravity. It's like a cosmic pressure cooker, constantly upping the ante. However, as we briefly touched on earlier, this stellar alchemy hits a brick wall when the core is filled with iron. Fusing iron requires energy rather than releasing it. It's a net energy drain, like trying to power your smartphone by eating it. At this critical point, the star's internal energy source essentially vanishes. There's no longer anything to push back against the gargantuan gravitational force of the overlying layers. And that's when the truly dramatic collapse begins. The iron core, now unsupported, implodes inwards at incredible speeds. We're talking about a collapse that happens in mere milliseconds, with material crashing down at a significant fraction of the speed of light. This implosion generates an enormous amount of heat and pressure. For stars of the right mass, this collapse is so intense that it overwhelms even the neutron degeneracy pressure that supports a neutron star. The core keeps shrinking, smaller and smaller, past the point of being a neutron star, until it theoretically becomes an infinitely dense point, the singularity. This catastrophic core collapse is usually accompanied by a Type II supernova explosion, often called a core collapse supernova. While the core collapses inwards to form the black hole, the outer layers of the star are violently ejected outwards, scattering newly forged heavy elements into space. It's a breathtaking duality: annihilation in the core, creation in the cosmic winds. This is a mainstream historical fact, observed indirectly through the study of supernova remnants and the detection of gravitational waves from merging black holes. Here's a quirky tidbit. Sometimes these massive stars are spinning very rapidly before they collapse. If a collapsing star is rotating fast enough, the supernova explosion might not be perfectly symmetrical. Instead, it can create incredibly powerful, highly focused jets of matter and energy blasting out from the poles of the collapsing star. These are thought to be the progenitors of long-duration gamma-ray bursts, the most powerful explosions in the universe after the Big Bang itself. So, a spinning stellar black hole might announce its birth with a blinding flash of gamma rays visible across billions of light years. Historians still argue about the precise mechanisms that generate these powerful jets and whether all such black hole formations produce GRBs. It's crucial to understand that not every supernova leaves behind a black hole. Many, as we discussed, leave behind neutron stars. The determining factor is the initial mass of the star. It's a finely tuned cosmic threshold. If the star is too small, like our Sun, it becomes a white dwarf. If it's moderately massive, it becomes a neutron star. And if it's truly enormous, exceeding that critical mass limit for neutron stars, then and only then does the core collapse completely into a black hole. So, the next time you look up at the night sky and see a brilliant star, remember that if it's one of those true behemoths, it's destined for a truly spectacular end. Our Sun, while vital to us, simply doesn't have the gravitational oomph to pull off this particular cosmic trick. It lacks the brute force required for its core to overcome all known pressures and shrink into a singularity. And that, in a comforting way, is a very good thing for us. Because next, we'll dive deeper into that elusive boundary around a black hole, the point of no return that truly define these cosmic titans.
All right, we've gone deep into the fiery creation of stellar black holes, birthed from the cataclysmic collapse of supermassive stars. Now let's focus on the feature that truly defines a black hole, the invisible boundary that marks the point of no return. We're about to define the Schwarzschild radius. It's the ultimate cosmic boundary line. Cross it, and you're officially on a one-way trip to oblivion. Imagine a black hole not as a drain in space, but as an incredibly deep, steep gravitational well. The Schwarzschild radius is simply the distance from the center of this well where the escape velocity exceeds the speed of light. Think about throwing a ball straight up in the air. If you throw it hard enough, it escapes Earth's gravity. If you throw it even harder, it could escape the sun's gravity. Now imagine a gravity so intense that even if you fired a beam of light straight out, it would curve back inward and fall. That critical distance, where light itself cannot escape, is the Schwarzschild radius. This boundary is also known as the event horizon. The concept was first calculated by German physicist Karl Schwarzschild in 1916, remarkably soon after Einstein published his general theory of relativity. It's a testament to the power of Einstein's equations that Schwarzschild was able to derive this solution, which described a perfectly spherical, non-rotating black hole. This is a mainstream historical fact, foundational to our understanding of black holes. His calculations showed that for any mass, there is a specific radius at which, if that mass were compressed into that sphere, it would become a black hole. So, how big is a Schwarzschild radius? It depends entirely on the mass of the object. For something with the mass of our Sun, its Schwarzschild radius is only about 3 kilometers, less than 2 miles. If you could somehow compress our entire Sun down to a sphere just 3 kilometers across, it would become a black hole. For Earth, the Schwarzschild radius is even smaller, less than a centimeter, or about the size of a marble. For a typical stellar mass black hole, say one that's 10 times the mass of our Sun, its Schwarzschild radius would be around 30 kilometers, about 18.6 miles, roughly the size of a very small city. Imagine a tiny sphere the size of a small town that contains the mass of 10 suns. That's the kind of density we're talking about. Crossing the event horizon isn't like hitting a brick wall. You wouldn't necessarily feel anything immediate as you crossed it. However, once you're inside, your future is irrevocably set. You are moving towards the singularity at the center, and there's no path that leads back out. Because information, including light, cannot escape from within the event horizon, it's impossible to observe anything that happens inside. For an outside observer, an object falling into a black hole would appear to slow down and get redder due to gravitational redshift, as it approaches the event horizon, eventually seeming to freeze and fade away at the edge, never truly crossing it from their perspective. It's a mind-bending consequence of warped space-time. Here's a quirky tidbit. While nothing can escape from inside the event horizon, black holes aren't entirely black in a way that Stephen Hawking famously pointed out. Through a process called Hawking radiation, black holes are theorized to slowly leak particles over vast amounts of time, evaporating. This is due to quantum effects near the event horizon. It's an incredibly slow process for stellar mass black holes, taking far, far longer than the current age of the universe for them to evaporate completely. So, while they're one-way doors, they do have a cosmic drip. Historians still argue whether Hawking radiation is a provable phenomenon or if there are alternative explanations for the theoretical energy loss of black holes. It's a debate that touches on the very edge of our understanding of quantum mechanics and gravity.
The existence of a Schwarzschild radius and the event horizon is what makes black holes so peculiar and so fascinating. It's a region where the rules we're familiar with break down, where time and space behave in ways that defy our everyday intuition. It's the ultimate cosmic boundary, a natural consequence of mass, gravity, and the fabric of space-time. And it's this very concept that solidifies why our sun will never become a black hole. It simply doesn't have the oomph to shrink down to its own Schwarzschild radius. We'll solidify that comforting thought in the next segment, exploring the crucial factor of our sun's mass.
All right, we've journeyed through the wild concepts of black holes and their enigmatic event horizons. Now, let's bring it all back home, literally to our very own star. The big question of tonight's journey: will the sun turn into a black hole one day? And the comforting, definitive answer is absolutely not. And the reason, as we've hinted at repeatedly, boils down to one simple yet incredibly significant factor: our sun's mass matters. You see, the universe plays by a very strict set of rules when it comes to stellar evolution, and mass is the master puppeteer. Every star's destiny, from its lifespan to its dramatic final act, is predetermined by how much stuff it started with. Our sun, while appearing huge and powerful from our vantage point here on Earth, is actually a relatively average-sized star in the grand cosmic scheme of things. It's what astronomers call a G-type main sequence star, often affectionately referred to as a yellow dwarf. Not a giant, not a supergiant, and certainly not a hypergiant. Just a dependable, medium-sized star. To become a black hole, a star needs to be truly gargantuan from the get-go. We're talking about an initial mass of at least 25 to 30 times the mass of our sun, as we discussed when talking about the formation of stellar black holes. Some theoretical models push this even higher, suggesting closer to 40 or even 50 solar masses might be required to ensure the core is massive enough to overcome all forms of degeneracy pressure and collapse into a singularity. Our sun, with its measly, by cosmic standards, single solar mass, simply doesn't have the gravitational horsepower to pull off such a feat. Think of it like this: becoming a black hole is like trying to squeeze an entire ocean into a teacup. You need an immense amount of pressure and force to make that happen. Our sun, when it eventually sheds its outer layers and collapses, will simply not have enough inherent gravitational pull left to overcome the electron degeneracy pressure that forms a white dwarf. Remember that electron pressure we talked about? It's like a quantum force field that resists further compression. For stars like our sun, that pressure is sufficient to halt the collapse. This is a mainstream historical fact, observed repeatedly in star clusters, where we see stars of different masses evolving along different paths. We have a robust understanding of stellar evolution, confirmed by decades of astrophysical observations and theoretical modeling. We know how stars are born, how they live, and how they die. And our sun fits perfectly into the category of stars destined to become white dwarfs. There's no magical loophole, no hidden clause in the cosmic contract that would allow our sun to suddenly become a black hole. Here's a quirky tidbit for you: the Chandrasekhar limit. Named after the brilliant Indian-American astrophysicist Subramanian Chandrasekhar, this limit specifies the maximum mass a white dwarf can have before electron degeneracy pressure fails. It's about 1.4 times the mass of our sun.
If a white dwarf gains more mass than this, perhaps by siphoning material from a companion star, as we briefly touched on, it will collapse further, either into a neutron star or, if even more massive, a black hole. Our Sun, even if it were to retain all its mass, which it won't due to red giant expansion, is right around that limit. But it won't actually collapse to a white dwarf at that mass. It will shed mass down to a core that is well below the Chandrasekhar limit. So it's not even a near miss. Historians still argue about the precise details of Chandrasekhar's initial calculations and the full implications of the limit, showcasing how even well-established scientific principles can have subtle nuances. So, when the Sun reaches the end of its life, it will calmly transition. It will expand into a red giant, as we've discussed, engulfing the inner planets. Then it will gracefully shed its outer layers, forming a beautiful planetary nebula. What will be left behind is its core, which will condense into a white dwarf. This white dwarf will be roughly the size of Earth, incredibly dense, and slowly, over trillions of years, it will cool down, eventually becoming a cold, dark lump of carbon and oxygen, a theoretical black dwarf. It's a peaceful, if slow, fade into cosmic retirement. No apocalyptic black hole, no gravitational vortex. This understanding provides a tremendous sense of cosmic perspective, doesn't it? While our Sun is the center of our lives, it's just one star among billions, following a very well-trodden path. It's not destined for the universe's most dramatic exit, and that's a good thing for our long-term, or at least Earth's long-term, cosmic safety. Knowing this, we can now appreciate the true mass threshold required for a star to achieve black hole status, which we'll explore in more detail next.
You're still drifting, probably feeling a bit more at ease now that we've firmly established our Sun is not going to turn into a terrifying cosmic vacuum cleaner. The key, as we've hammered home, is its relatively modest mass. But if our Sun is too small, what is the mass threshold for collapse into a black hole? What kind of cosmic heavyweight do you need to pull off such a dramatic, space-time bending feat? The critical mass for a star to end its life as a black hole is not a single, universally agreed-upon number, because it depends on several complex factors, including the star's initial chemical composition and its rate of rotation. However, the general consensus among astrophysicists, and a mainstream historical fact, is that a star needs to start its life with an initial mass of at least 25 to 30 times that of our Sun to reliably form a stellar mass black hole. Some models even push this initial mass much higher, closer to 40 or 50 solar masses, especially if the star sheds a lot of its mass during its lifetime, which many massive stars do through powerful stellar winds. Why such a high threshold? It all comes back to the core that's left behind after the star has exhausted its nuclear fuel and undergone its supernova explosion. For a star to become a black hole, this remnant core must be massive enough to overcome what's called neutron degeneracy pressure. Remember that for a white dwarf, electron degeneracy pressure halts the collapse. For a neutron star, the protons and electrons have been squeezed together to form neutrons, and it's the neutron degeneracy pressure that provides the outward push. But if the core is too massive, even this incredible force isn't enough. The theoretical limit for a neutron star's mass is known as the Tolman-Oppenheimer-Volkoff limit, which is generally estimated to be around 2 to 3 times the mass of our Sun. If the remnant core left after a supernova explosion exceeds this TOV limit, then neutron degeneracy pressure fails, and the collapse continues unabated. There's nothing left to stop it, and it shrinks infinitely, forming a singularity and thus a black hole. So, a star that starts at, say, 30 solar masses might shed a lot of that mass during its life, but its core would still be massive enough, above 2 to 3 solar masses, to collapse into a black hole.
Think of it like building a Jenga tower. For a white dwarf, you've removed some blocks, but it's stable. For a neutron star, you've removed more blocks, and it's incredibly dense but still standing. But if you take out too many blocks, or if you started with a much taller tower, it eventually becomes so top-heavy and unstable that it collapses completely, no matter how carefully you try to balance it. That final, irreversible collapse is the birth of a black hole. Here's a quirky tidbit. There's a theoretical mass gap that scientists are still exploring. It's thought that there's a range of masses for stellar remnants where neither a neutron star nor a black hole is typically formed. For example, if a star's core remnant is too heavy for a neutron star, above the TOV limit, but perhaps not heavy enough to form a standard stellar black hole through a direct collapse, what happens? Some theories suggest that very massive stars might undergo something called a pulsational pair instability supernova, where they explosively shed their outer layers in repeated bursts before finally collapsing, potentially leaving behind or nothing at all, depending on the remaining mass. Historians still argue whether this mass gap is real, or if it's simply a result of our current observational limitations and theoretical models. It's a fascinating area of ongoing research, pushing the boundaries of our understanding of extreme stellar deaths. So, for our Sun, with its relatively puny single solar mass, collapsing into a black hole is just not in its stellar playbook. It will gently swell, gracefully shed, and eventually cool. The stars that do become black holes are the true behemoths, the ones that push the very limits of stellar existence. They are the stars that burn brightest and fastest, living intensely before their cataclysmic demise, leaving behind the ultimate testament to gravity's power. Knowing this threshold helps us understand why the universe has so many white dwarfs and neutron stars, but relatively few stellar mass black holes. Only the most extreme stellar lives lead to such an exotic end. And speaking of exotic ends, let's briefly touch upon other rare or theoretical stellar remnants that exist beyond our familiar categories.
Okay, we've firmly established the Sun's safe white dwarf destiny and the colossal mass required for a star to become a black hole. But the universe, bless its quirky heart, is full of surprises, and stellar evolution sometimes throws us a curveball. While white dwarfs, neutron stars, and stellar black holes are the most common end states for stars, there are also exotic stellar remnants, theoretical or extremely rare objects that push the boundaries of our understanding. These are the deep cuts of cosmic categorization, the ones that make astronomers furrow their brows and scribble furiously on whiteboards. First, let's circle back to that idea of a black dwarf. We talked about how our white dwarf sun will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark, inert lump of degenerate matter. It's a mainstream historical fact that the existence of black dwarfs is currently purely hypothetical. The universe isn't old enough for any white dwarf, even the very first ones that formed, to have completely cooled down to this theoretical state. They are literally cooler than a cosmic cucumber, just waiting for billions more years to pass. Imagine waiting that long for a delivery. But they are the logical endpoint of white dwarf evolution, a testament to the immense timescales involved in cosmic processes. Then there's the intriguing, albeit highly speculative, concept of a quark star, or strange star. Remember how neutron stars are so dense that protons and electrons are crushed into neutrons? Well, theory suggests that if a neutron star's core were under even greater pressure than usual, the neutrons themselves might break down into their constituent fundamental particles,
quarks. These quarks, normally confined within protons and neutrons, would then form a new exotic state of matter called quark-gluon plasma, or strange quark matter. A star made of this would be even denser than a neutron star. It's like trying to pack more into your suitcase after you've already crammed it full. You start breaking down the clothes themselves. Here's a quirky tidbit. While no quark stars have been definitively identified, some anomalous pulsars, or particularly compact neutron stars, have been proposed as candidates. It's an active area of research, where observations are constantly trying to catch up with the wilder theoretical predictions. Historians still argue whether there is sufficient observational evidence to definitively confirm the existence of quark stars, or if current anomalies can be explained by existing neutron star models. It's a classic scientific chicken or egg debate. Moving to the extreme end, there are theoretical objects related to black holes, but with different properties. For instance, some theories propose naked singularities. A singularity, as we discussed, is the infinitely dense point at the center of a black hole. In a typical black hole, this singularity is always hidden behind an event horizon, making it clothed and inaccessible to outside observation. But a naked singularity would be a singularity without an event horizon, meaning you could theoretically observe it directly. This would break many of our current laws of physics, as information could escape from an infinitely dense point. Most physicists believe that cosmic censorship hypothesis prevents naked singularities from forming in our universe. But it's a fascinating, if unsettling, thought experiment. Another fascinating, albeit less likely for stellar remnants, is the idea of boson stars, or fermion balls, which are purely theoretical constructs of exotic particles. Or even magnetars, which are a type of neutron star with incredibly powerful magnetic fields, billions of times stronger than any magnet on Earth, capable of stripping the data off your credit card from across the galaxy. Okay, maybe not that last part, but their magnetic fields are truly mind-boggling, causing tremendous bursts of X-rays and gamma rays. They're essentially neutron stars on cosmic steroids, exhibiting extreme magnetic activity. These exotic remnants are rare, theoretical, or represent extreme variations of more common objects. They highlight how much we still have to learn about the universe and the ultimate fate of matter under the most extreme conditions. Our cosmic picture is constantly evolving, with new discoveries and theoretical advancements challenging our existing frameworks. But for our sun, none of these wild cards apply. It's on a well-worn path to a comfortable, if incredibly dense, retirement. And as we consider these bizarre possibilities, it's worth taking a step back and really appreciate the immense cosmic scale of time that underpins all these stellar dramas. That's our next ponderance.
We've journeyed from the sun's present calm to its fiery red giant phase, past white dwarfs, neutron stars, and the gravitational maw of black holes, even touching on some truly exotic stellar leftovers. All of these transformations, from the birth of a star to its eventual demise, unfold over timescales that are almost impossible for the human mind to grasp. It's time to truly reflect on the cosmic scale of time, because without understanding these vast durations, the stories of stars are just abstract concepts. Think about your own life, say 80 years. That feels like a long time, doesn't it? Now imagine that our entire sun has a lifespan of about 10 billion years. Your 80 years is less than 1/billionth of the sun's life. It's like trying to represent the entire history of Canada, which, from its confederation in 1867, is only about 158 years old here in Toronto, by a single blink of an eye. The comparison just doesn't work.
The universe itself is a grand old dame, currently estimated to be around 13.8 billion years old. Our Sun, at 4.6 billion years old, is roughly in its middle age. It was born when the universe was already a substantial teenager. It has another 5 to 6 billion years of stable main sequence life ahead of it. Imagine that! For every year you've been alive, the Sun has been burning steadily for millions of years. It's a mainstream historical fact that the concept of deep time in geology and cosmology revolutionized scientific thought, moving us away from anthropocentric views of time that confined the universe's age to mere thousands of years. Consider the process of stellar formation. Those vast nebulae of gas and dust, they can take hundreds of thousands to millions of years to collapse and ignite a protostar. Then, the main sequence phase for a sun-like star lasts for billions of years. The red giant phase, that dramatic planet-swallowing expansion, only lasts for a few 100 million years. And the long, slow cooling of a white dwarf into a theoretical black dwarf, that's trillions of years, far, far longer than the current age of the universe. Even the evaporation of a stellar mass black hole via Hawking radiation would take an unfathomable 100 years. That's a 1 followed by 67 zeros. By that point, the concept of time itself might be something entirely different. These timescales dwarf human existence, historical records, and even geological epics. They make the rise and fall of civilizations, the formation of mountain ranges, and the very evolution of life on Earth seem like fleeting moments, a quick flash in the pan. We are living on a planet that orbits a star that is in its stable, mature phase. We are, by cosmic standards, incredibly fortunate to be here now. Here's a quirky tidbit. The fastest recorded star, S4716, orbits the supermassive black hole at the center of our galaxy, Sagittarius A, at about 8,000 kilometers per second, completing an orbit in only 4 years. Contrast that with our own Sun, which takes about 230 million years to complete one orbit around the galactic center. Even at those incredible speeds, it still takes vast amounts of time for cosmic events to unfold. It highlights the extremes of velocity and scale within our galaxy alone. Historians still argue whether the precise measurements of stellar orbits around Sagittarius A provide definitive proof of a supermassive black hole, or if other extremely dense objects could explain the observations, though the black hole theory is overwhelmingly favored. Understanding these timescales gives us a profound perspective on our place in the universe. It reminds us that while our lives are incredibly precious, they are part of a much, much larger, slow-moving cosmic drama. The processes we've discussed tonight, stellar births, lives, and deaths, are not quick events. They are the slow, majestic unfolding of astrophysical laws across durations that stretch our imaginations to their breaking point. So, as you lie there, contemplating billions and trillions of years, perhaps you feel a little less anxious about the Sun becoming a black hole and a little more awestruck by the sheer patience of the cosmos. The universe isn't in a hurry. It takes its sweet time, molding stars, creating elements, and eventually fostering conditions for life, all on timescales that redefine what long truly means. This journey through cosmic time naturally leads us to our final contemplation, the far, far future of the universe itself. What happens when all the stars have faded, and what becomes of everything?
You're almost there. Nestled deep in the quiet, hopefully no longer worried about the Sun's gravitational aspirations. We've stretched our minds across cosmic distances and mind-boggling timescales.
Now for our final act, let's gaze into the far, far, far distant future of the universe. What happens after all the stars have burned out, all the black holes have evaporated, and the last vestiges of energy have dissipated? It's a concept often called the heat death of the universe, and it's a curiously calming, if profoundly quiet, end. First, let's recap our cosmic timeline, specifically for stellar objects. Our Sun will become a white dwarf in about 5 to 6 billion years. White dwarfs will continue to cool for trillions of years, eventually, theoretically, becoming cold, dark black dwarfs. Even the longest-lived red dwarf stars, those incredibly frugal little cosmic embers, will eventually exhaust their fuel after hundreds of billions, even trillions of years. So, in this incredibly distant future, the era of star formation and shining stars will come to an end. The universe will become a much, much darker place. The last remaining light sources will be the dimming black dwarfs, the occasional burst from a merging neutron star, or the brief, powerful flash of a black hole consuming matter. Then come the black holes. While stellar mass black holes are the ultimate gravitational traps, even they are not eternal. As we briefly touched upon, theory suggests that black holes slowly evaporate over incomprehensibly long timescales through Hawking radiation. For a stellar mass black hole, this process takes 10 years. For the supermassive black holes at the centers of galaxies, it's even longer, potentially 10 trillion years. That number is a 1 followed by 100 zeros. To put that in perspective, there are only about 10 atoms in the observable universe. So, eventually, even these cosmic leviathans will have radiated away all their mass and energy, disappearing into nothingness. It's a mainstream historical fact that Hawking's theoretical prediction of black hole evaporation, though unobserved directly, is a cornerstone of modern quantum gravity research. So, in this unimaginably distant future, we're left with a universe that is incredibly cold, dark, and dilute. All the stars are gone. All the black holes are gone. What's left? Mostly elementary particles, photons, neutrinos, and possibly electrons and positrons, scattered incredibly thinly across an ever-expanding, increasingly empty cosmos. Even protons, thought to be stable, might eventually decay, over timescales far exceeding the age of the universe. Current experiments place their half-life at more than 10 trillion years. If protons decay, then all matter as we know it will eventually dissolve. The universe will be so vast and empty that the average distance between any two remaining particles will be enormous. There will be no energy gradients, no temperature differences, no forces acting to create anything new. This is the heat death of the universe, a state of maximum entropy where all energy is evenly distributed and nothing more can happen. It's not a dramatic explosion or a sudden collapse. It's a slow, quiet fade into ultimate equilibrium. Here's a quirky tidbit. Some very speculative theories suggest that even in this ultimate emptiness, something new might eventually emerge. Perhaps through quantum fluctuations over truly absurd timescales, a new Big Bang could spontaneously occur, birthing a new universe from the vacuum. Or maybe the expansion of the universe could eventually reverse, leading to a big crunch, though current evidence overwhelmingly points to accelerating expansion. Historians still argue whether the heat death is the only possible ultimate fate for the universe, or if exotic physics, currently unknown, might lead to other scenarios. It's a philosophical and scientific debate that keeps cosmologists up at night. As you lie there, feeling the warmth of your covers, imagine that ultimate quiet. No light, no heat, no movement, just an endless, vast expanse of almost nothing. It's a profound thought, not terrifying, but rather humbling. It reminds us of the fleeting, precious nature of the present moment, this era of stars and galaxies and life. But that's billions upon billions of years away, far beyond the lifespan of anything we can truly comprehend. For now, our sun continues to shine, a stable, life-giving force. Our planet orbits it faithfully, and you are here, listening to these cosmic tales, a tiny, intricate part of this incredible, ongoing universe. So, let that immense time scale wash over you. Let the thought of a universe so quiet, so empty, slowly bring a sense of peace. Your sun is not turning into a black hole. It will live a long, full life, transforming into a gentle white dwarf. The universe, while grand and full of dramatic ends for some stars, has a calming, slow journey ahead for itself. There's no rush, just the slow, steady march of cosmic time. Breathe deeply, feel the stillness. The stars are out there, living their lives, and so are you. Rest easy under the vast, patient sky.